Hi everyone, I am Muthiah. I am a Ph.D. student in the Department of Electronic Systems Engineering at IISc. In this presentation, I am going to talk about why field programmable analog array can be a suitable candidate for implementing machine learning tasks and also for neuromorphic computing. I will give you a quick overview of what neuromorphic computing is all about. Neuromorphic computing in simple term means brain inspired computing. So here we don't aim to imitate each and every cell that we have in the brain. Instead, we try to look for the organizing principles of how computation is carried out in the brain. If you take a look at this bee, which is flying around between different flowers looking for food, it exhibits a bunch of really interesting behavior. Like it flies acrobatically, it recognizes patterns, so it knows where the flowers are. It navigates from its home to where the food is. It forages for food and then it communicates the information about where the food source is back to the nest. It does everything by consuming only 20 milliwatts of power. So neuromorphic engineering is inspired by such kinds of biological systems. In artificial intelligence, we are exploring the different kinds of algorithms to improve the computational efficiency. But it is very easy to lose sight of the fact that whatever algorithms we come up with, finally we are going to have to implement them on the real hardware. So it's really important to think about not only the what algorithms to build, obviously that is super important, but we also have to think about how can we possibly deploy these algorithms on the hardware in a power constrained way. So our aim is to build a power efficient hardware which can implement such ML algorithms. For doing so, we are preferring analog computing over digital computing. Why? Because in order to implement a 8-bit digital multiplication, we might need several thousands of transistors in order to do so. So that will require a lot of power and energy. So we can implement the same using an analog multiplier which requires only 8 transistors. So that is the inherent advantage that we have in case of analog computing. That's why analog computing is preferred over digital computing, which because it exploits the physics of the device by doing these computations. So the problem statement is to come up with a system level architecture for our FPAA, which must be scalable and reconfigurable at the same time. One of the other challenges that we might face while that we could face while implementing this FPAA system is a analog signal integrity issue. So we know that analog signals are very prone to noise, offsets, error because of the a natural mismatch between the devices. No two devices can be made, no two transistors can be made with absolute matching. See, other problem could be the implementing asynchronous system. If we can implement the asynchronous system, that will save a lot of energy and power overhead. But implementing that is a real challenge. So, at the heart of our computational unit, we have something known as margin propagation that is highly optimized for this neuromorphic computing task. So we are essentially trying to map these neural networks onto our FPAA, right? So vector matrix multiplication is basically the fundamental computational block that every neural network does. So this our FPAA act like an ML accelerator, which could accelerate this vector multiplication application process. So yet other problem we could face while doing this is the routing issue. So if you suppose, let's say I want to connect route this pin 3 from cab 1 to pin 9 of cab 3. This cannot be done directly. This can be done only by means of the routing channels. So also whenever if I wanted to switch the direction from from vertical to horizontal or vice versa, that can be achieved only by means of a switch block. So this problem could be essentially converted into a graph problem, and which then can be solved by using algorithms such as Dijkstra and so on. So I will quickly show a demo using a tool called VTR, which stands for Verilog to Routing. VTR is built for mainly for digital FPGA workflows, but the same underlying concept used for placement and route can be adopted here as well, or extended to model alternative architectures such as FPAS. So in a digital standard FPGA flow, each tile features a configurable logic block, which is called a CLB here. Here in FPAA, we will be replacing the CLB with a configurable analog block, which will house the analog computational elements instead of digital lookup tables. So this is a primary distinction between the our FPAA and a traditional FPGA. So we are, I'll show you how this routing actually works. So when I enable these nodes, these are nothing but the routing channels which are running between these computational tiles. So when I enable the switch blocks, you can see how the switch bus is implemented here, which enable us to switch the direction from vertical to horizontal and vice versa. When I enable the connection box, you can see how the connection box is implemented here. So the core steps like placement and route remain largely unchanged here. So that's why we can leverage the same place and route methodology used for FPGAs in FPAA as well. So this is how our final chip would look like. This is going to be a analog counterpart of FPGA. You can also see the I/O pads, the input output pads placed along the corners of our FPAA chip. So this is how our final product would look like. Thank you.